Well, thank you for showing up at this point. Still some more people have signed up who haven't been here, but I'm going to start the meeting anyway, just to begin to be on time. I'm going to, first of all, thank our speaker and the societies who are putting this on and all of you who attend. I'm Tom Kaminsky with the IEEE Madison section. I do some of the technical activities coordinating and the newsletter. If anybody would like to pick up the newsletter, I'd love to give it over to someone. But of course, everyone's going to shake their head no and say no. What I'm going to do now is officially transfer the meeting to Dennis and let Dennis introduce the speaker.
Okay, tonight's speaker is Dr. Bhuvana Krishnaswamy. She is currently an assistant professor in electrical engineering at the University of Wisconsin. She got her bachelor's degree in India and her master's and PhD from the Georgia Institute of Technology in Atlanta. She has won a number of awards since she's been here. She's been here only since 2018, just a few years. She currently has 17 patents, 2 patents, I'm sorry, and 17 publications of various kinds, and has given about 7 or 8 different talks in those couple of years. So, and her course she just finished teaching was ECE 901, Advanced Topics in Wireless Networks and Sensing. So tonight, our speaker is going to speak on fundamental challenges of low power wide area networks.
Thanks so much for the introduction, Dennis. And in fact, I want to thank you for reaching out and inviting me to this meeting. Honestly, I wasn't aware of IEEE meetings with regular speakers until now, and I'll try to be an active member. I think there's a great way to meet people in the community, in physical neighborhood, and especially the first few minutes of discussion on new areas and people's expertise in new areas is a great way to learn new topics too. I think I'd love to take all of your advice and feedback on some of the projects we are taking on. So today's presentation, particularly, I want to talk about 2 of the most recent works from my lab, and both of them in the context of low power wireless networks. So this is a collection of 2 distinct topics in the broad area of low power wireless networks. And the talk is titled Fundamental Challenges because this is seemingly solved area of low power and wireless communication has gotten attention in the recent past for some of the challenges that we'll discuss today and see why there are fundamental bottlenecks and how to overcome some of them, some of the tools that we have used, some of the tools that are potentially available that we are going to explore in the future, and get your thoughts on that and have some conversation about it. So let me try and share my screen first. One second. Okay, so I'm guessing you can see my screen now, and the PowerPoint slide and not the presenter view. Can someone just let me know if that is the right screen you're looking at?
We can see it. Okay,
that's good. So as Dennis pointed out, I'm Bhuvana Krishnaswamy. I'm an assistant professor in the Department of Electrical and Computer Engineering at UW-Madison. So the title of today's topic is Fundamental Challenges in Low Power Wide Area Networks, right? So I thought I'll start with some definitions of low power wide area networks, which is LPWANs for short. LPWANs, I think wireless networks has been around in the past 2-3 decades now, and plenty of research has gone into wireless communication starting from cellular networks, in fact, starting from satellite networks, cellular networks, more recently, Wi-Fi got a lot of attention, Bluetooth are some of the wireless networks that we are familiar with that we use in our daily life. But low power wide area networks, or LPWANs, have become a necessity and has been starting getting some attention in the recent past due to plenty of applications that need the 4 features that we are looking in the screen now, which are long range, which is long distance for communication, long battery life for the transmitter devices, wide area coverage, meaning large number of devices to coexist, and most importantly, low cost. So to give a sense of some of the applications that drove the need for LPWANs, and one of the most common applications where the problems that we are going to discuss today and companies that have come out of LPWANs are targeting would include smart agriculture, where you have sensors deployed in a large farm or a large field, collecting soil health metrics like soil moisture, temperature, carbon dioxide levels, and so on, and convey this information to a cloud server in real time. Or smart homes are relatively less have less needs in the context of LPWANs, but have a lot of applications in this context. But smart cities is another example of LPWANs. We have needs for long range communication where devices are in remote locations and have number of devices. So in many of these applications, you see the need for the 4 bullet points that we have on top, right? Which is, we are looking at sensors deployed in remote fields or remote areas, and therefore we need the sensors or the IoT devices to have a long battery life so that we don't have to keep going back for replacing batteries or replacing the whole device. Or an alternative is higher cost for solar panels to recharge the device continuously. And these are long range because we want to reduce cost on deployment. If we were to put a Wi-Fi access point in a field, we need multiple Wi-Fi access points, each of them talking to another access point, and so on and on, leading to a much larger infrastructure cost. So to reduce the cost, typically LPWANs have a star topology, meaning we have a slide. I have a slide on that, but a star topology with multiple sensors talking to one gateway, and the gateway would talk to the internet infrastructure, let's say. So because of this reduced need for the need for reduced cost, we typically prefer an infrastructure that has last mile technology, which is multiple devices talking to single gateway. And wide area coverage again comes from the need for hundreds to thousands of devices deployed in a large area and being able to collect data from all of them in real time. Excuse me. So like I said before, the need drove, excuse me, I think I need this here. So LPWANs are an area that were driven by some of the applications that we are looking at here, right? So because of those needs and the scope for customer base, a number of companies have come up in the recent past. So the companies that we see here, NB-IoT, LoRa, SigFox, have come up in the last 5 to 10 years, targeting just these applications, which is smart agriculture, smart homes, among many others, but in the context of low power wide area networks. So let's look at one such example application of a smart farm with sensors deployed in the field and one gateway or one receiver to which all the sensors are sending data. So one of my collaborators is in the Department of Soil Science here in UW-Madison, and we are working on a real-world deployment where we have put together a soil moisture, pressure, and carbon dioxide sensor in a single module with a wireless communication device on top of that, which conveys data. It collects every 10 minutes. So every 10 minutes, all the devices wake up, measures from these 3 sensors, and transmit wirelessly to a remote device. Although we have a person with a tablet here, let's assume this person is replaced by a gateway. So there are hundreds of devices in a large field talking to a single gateway, deployed in remote areas that we may not go and change the batteries regularly. So I just want to bring our attention to what each such sensor would look like. So here is a picture from one of the research papers, but one of the modules that we are building now looks very much like this, which is a weatherproof box with sensors inside and a wireless device with a radio outside that's going to communicate data wirelessly to a remote device. And the wireless part is important because people are interested in getting this data in real time. So one of the reasons low power wide area networks became a necessity, or the question of wide area networks being about a new problem in wireless communication came about because of this architecture and some of the numbers that we see here. So here is an illustration of what a sensor module / IoT device would look like in an LPWAN network, let's say. There's a battery that powers the device, a sensor that feeds the data to our microcontroller. The microcontroller has memory, it processes data it receives and communicates through an interface to a wireless transceiver, which then sends it wirelessly over a radio. But if we look at the power consumption of each of those modules, all of these blocks combined can be put together in a microcontroller. And we measured in our lab the current consumed by this device, 2 example microcontrollers. These are some of the state-of-the-art low-power microcontrollers. They consume in their active mode 1 milliamp, and all of them operating around 3 to 5 watts. So let's assume the voltage is the same. They draw active current of 1 milliamp, and when they sleep, they consume about tens of nanoamps. On the other hand, a wireless module, and once again, these are some of the state-of-the-art low-power wireless modules designed specifically for IoT devices. Even in their lowest current consumption, when we operate at the smallest transmit power, their active current is in the order of tens of milliamps. Their sleep current are comparable, but the active mode, when they're actively transmitting, they are an order of magnitude more power consuming than the microcontroller. So one of the inferences that we made from this exercise was that in an IoT device or in a low power wide area network, radio is the bottleneck when it comes to energy consumption. That is, computing has become more and more efficient as we grow smaller and smaller in our microcontrollers, that they've become extremely efficient in performing all the computations that we need at low current consumption. Whereas wireless module, the transceiver that we see here, that still consumes more power than everything put together ahead of that. So if we were to design an energy efficient IoT device that can communicate data to a remote server in real time, then we need to conserve the energy of the radio module or the wireless module. So that really drove us to identifying the challenges in designing low power wireless networks. So to get a sense of what is all out there are plenty of wireless technologies that have been developed, like we discussed early on, right? So we want to first see what is all there and what is missing. So here is an illustration of some of the wireless technologies that some of the popular wireless technologies. The trade-off here being communication range versus power consumption. So the reason we picked these 2 metrics to compare existing technologies is that these are two of the most common requirements for LPWANs, which is low power and long range communication. So if we look at extremely low power devices like RFID tags or Bluetooth devices, they are extremely low power. Some are batteryless like RFIDs, but they operate at very small range. The communication distance is very small. So if we were to reach long range communication, we can't use some of these batteryless or low power devices. As we go higher in range, we have Wi-Fi that goes up to few meters and cellular networks that goes to a few kilometers, in fact. But their downside is they consume a lot of power, that you cannot have a Wi-Fi or a cellular device out there without a battery that can survive, with a battery that can survive for months together. On the other extreme, like I mentioned earlier, there have been few companies, few technologies for that matter, not just techniques, fundamental technology that have developed in the recent past that can achieve long range to support LPWANs at the cost of relatively high power, but they manage to provide long battery lives by letting devices talk for fewer and fewer amount of time. So by limiting their duty cycle, LoRa, NB-IoT, SigFox, some of the new technologies conserve the battery life, but they're still high power consuming technologies. So you notice different colors being used in this figure. I'm not going into specifics of that, but different color indicates data rate as well. So I see some questions, but I think I'll get to questions in the end if that's okay with everyone. Okay, so the data rates that the color that you see here represent data rate in that some of the technologies we are talking about range versus power, but they also compromise on communication rates or data rates. And we'll see that in just a few slides down the road. Excuse me. So the goal of this talk is to see, is there room to innovate and answer the question and find this bubble? Oh, I forgot to mention the size of the bubble is the wide area deployment, meaning how many devices can I support in a network, in a single network. So the larger the bubble is, more devices I can support in a network. So one of the questions that we ask in my lab is, can we come up with wireless communication algorithms that can offer long range at low to no power consumption, and yet accommodate hundreds of devices, meaning large deployments. But there is no free lunch, right? We have to compromise on something, but we are saying let's compromise on data rate in that we will support hundreds of devices, but each device would only transmit few tens to hundreds of kilobits per second, or few to tens to hundreds of bits per second in some cases. And that is okay in an LPWAN because most of the applications that again drove the field of LPWANs are in the field of monitoring applications where we don't typically end up transmitting streams of data like video streaming or audio streaming. These are few data bytes, pockets of data that are being sent every few seconds. So they are resilient to data rate, low data rates, because they're not transmitting large file sizes. So we take the opportunity of low data rate needs of each of these applications and see if we can get a network which can support a large number of devices over a long communication distance at low power. So before we go into some of the solutions that we came up in my lab, let me just walk us through why this trade-off that we saw in the previous slide exists in first place. So all of that I want to link to one metric or one metric of interest called bandwidth. I think a lot of us are familiar with RF bandwidth. I want to link all the features of interest that we saw in our earlier slides to bandwidth. So I think to some of us, it might be obvious that if you use a lower bandwidth of communication, the range of communication is very high. And then I would love to talk to you if this is of interest and would like to know more about why that is the case. Let's assume for now this is true, that narrow bandwidth at the receiver end, smaller and smaller bandwidth would allow us to increase the range of communication. On the other hand, if we increase our bandwidth, the range of communication would decrease. there are a few other relations to bandwidth as well. If our bandwidth is low, our data rate would be low because the range of frequencies that's available to us for communication is small, and therefore data rate would be small. On the other hand, if our bandwidth is high, our data rate can be high. So what does data rate low mean? If I'm sending the same file at a smaller rate, I'm going to need my radio to be on for a longer duration of time because it's going to take me longer time to send the same file if I'm sending it slow. So time on air, which just boils down to the amount of time my radio is going to be on, will increase if my bandwidth is small. And if my time on air is long, we already saw that radio consumes higher energy than the microcontroller does. And therefore, if my radio is on for a longer duration, the battery life is going to decrease. So right here, we are seeing a contrast in needs to bandwidth, in the need, in the relation to bandwidth, which is if I want long range communication, I would desire a narrow bandwidth. But if I need longer battery life, if I need my battery life to be high, I would like my bandwidth to be high. So if I need range and long range and high battery life, I need to find a bandwidth that satisfies both of them. Now let's bring the third metric of interest, which is wide area. So wide area would mean I have large number of devices that I have to accommodate. That translates to I have large number of devices that I have to accommodate without two nodes colliding with each other at the same time. Because we're talking about wireless networks, two nodes, multiple nodes share the same wireless medium. Therefore, when they are transmitting data without each other's, without any coordination, they are going to collide with each other. So if my bandwidth is small, let's look at this case, bandwidth is small, my duration is high. If I'm speaking for a long duration, the probability of someone else trying to speak at the same time is going to be high as well. And therefore, the probability of collisions would be high. So if my bandwidth is small, my collisions would be high. So that brings a third contrast to my bandwidth, right? If I need high battery life, my bandwidth has to be high, but I want my probability of collisions to be small, then also my bandwidth needs to be high. So there are three contrasting requirements to bandwidth. Of course, two of them are the same, meaning if I need long range and long battery life and fewer collisions, I would like to have a larger bandwidth. But getting all three of them is impossible, seemingly impossible. And that's really the fundamental bottleneck to getting all of the factors that we desire for an LPWAN, which is a long range, long battery life, and fewer collisions of wireless devices operating simultaneously. So I think before I go to solutions, maybe I can try to answer some of the questions. Actually, let me do that in the end, if that's okay. I'm having a tough time navigating between chat and the slides.
I am recording the questions on a written form, so I'll have them back for you.
Okay, okay, that's good. Thanks. Yeah, so I want to talk about one of the solutions that we came up with to overcome this contrasting relationship between range, bandwidth, energy and bandwidth, probability of collisions and bandwidth. And we called it Y chronos. Chronos is a term for time. So we'll see why that is appropriate for the solution that we proposed. But we came up with a modulation technique which can offer these three features that we talked about at the cost of data rate. Let's look at how we're able to achieve that. So if we were to look at a conventional modulation technique, which is something like a frequency shift keying or any energy-based modulation, rather quadrature amplitude modulation are some examples of modulation techniques that we typically use in Wi-Fi or cellular networks, which goes something like this. There is a physical layer header, which tells us when packet is received or when a packet is in the air. So me as a receiver would look for this physical layer header to understand when I'm receiving a packet, and I'll continue to read for the rest of the packet, and followed by the header is the actual data which is sent through bits. Whereas our proposed solution, Y Chronos, we are saying let's convey information in the time interval between two short messages. So analogy that I love to give for this solution is when we are talking to each other, when we are saying, I'm going to explain everything I know through words to whoever I'm talking to, would be equivalent to an energy-based modulation / conventional modulation, where whatever data I have to send is sent as bits, which is then mapped to electromagnetic signals, which are then sent through air. Whereas Y Chronos would be an energy efficient modulation where I'm not speaking much, I'm saying just few short words, and the silence the silent period between my two short words would convey all the information I have to send. So let's take an example that I have let's say I have a temperature sensor whose output is a value of 678, or a pressure sensor whose value is whose output is an integer value of 678. So if I were to use an energy-based modulation, I would map 678 to bit sequence and then send them as EM signals. Whereas our proposed solution, which is Y Chronos, would send a short message, which we call a preamble, which is still an EM signal with few bits of message, but predetermined short message. And after sending that message, I'll just remain silent for 678 clock cycles. There's a made-up number, obviously. How we map data to this number is a problem on its own. But let's say the data that we want to send to 678, instead of mapping 678 to bit sequence, I'm going to wait for 678 clock cycles, and I'll send a stop or a post-amble message as soon as my clock timer expires. So the assumption here is my receiver, who's constantly listening to signals in air, as soon as my receiver sees this preamble message, it will trigger a clock at its end. It will start counting for at the same clock rate as I have. So during system setup, we both agree on a clock rate, and we both start counting as soon as we send or receive the preamble. And as soon as the receiver sees a post-amble, it will stop counting. So in an ideal network without any clock skews or any timing errors, if both of us started counting and stopped counting when we saw preamble and post-amble, the value 678 is known to both the transmitter and receiver. But the amount of time or the words that I've spoken is significantly smaller in Y Chronos as compared to energy-based modulations. So an energy-based modulation, just to remind, has to be on for this entire duration, as opposed to Y Chronos, who's going to be on only for preamble and post-amble. So here is where we adjust the first concern of bandwidth and time on air relation. So the energy-based modulation that we see here, any energy-based modulation for that matter, FSK, QPSK, QAM, and so on, we'll if we have longer and longer data to send, whether it's 678 or 10,000, the more data we have to send, the longer is my data and the longer is my radio on to send that information. Whereas in a modulation where we are conveying information in the time between two short messages, however long is my information, I'm only going to send this preamble and post-amble into the wireless medium. The rest of the time when I'm actually conveying information, I'm not sending any active signals into the wireless medium. So now the first relation that we saw, which is time on air being high if my bandwidth is low, is that relationship is broken in this modulation technique, because irrespective of my data, I'm only going to send this amount of information over the wireless medium. Therefore, irrespective of my bandwidth, or it's still dependent on bandwidth, but duration it takes for me to send a data is not a function of my data, and therefore it's not a function of the bandwidth. The overall duration is a constant, which is the sum of preamble and postamble messages. So my energy consumption, me as a Y Chronos transmitter, only depends on how long and the format of my preamble and postamble messages. So by separating time on air and the duration of my message, Y Chronos is able to separate the relationship between bandwidth and time on air. And that's what we leverage in reducing the energy consumption of an IoT device, wireless IoT device. We call these preamble and postambles as anchor symbols because they are anchoring the message that we want to send. So it's important to design the best anchor symbols that satisfy some of the criteria, right? So if we look at this picture, if I have longer and longer anchor symbols, the energy consumed by my IoT device is going to be higher and higher. So I would like the anchor symbol to be as short as it can get so that the energy consumption is low. But if I send too short a message, it might get lost in my wireless transmission. So I want to choose an anchor symbol that has very low probability of false positives, meaning it shouldn't trigger my receiver to start counting or stop counting erroneously. So we want to have a low probability of error. So I want to have an anchor symbol that doesn't trigger my receiver to start or stop counting. At the same time, so the red curve is the probability of false positives, and the black curve is the probability of symbol errors. I want to send short enough symbols that can be correctly decoded by my receiver. So depending on the channel that we are operating, depending on how the anchor symbols are being sent over air, we can find certain optimum points where I can choose an anchor symbol length which satisfy my required probability of anchor symbol errors and required probability of false positive rate. So the blue circle that we've marked, which is approximately 11 bits, these were the numbers that worked well for some of the environments that we were looking at when we were sending these bits using frequency shift keying. So just to refresh, we send short messages using frequency shift keying, and those messages are like start and stop messages. So when I send a predetermined 11-bit sequence, in this example 11-bit sequence, my receiver on seeing the 11 bits understands that I'm the one transmitting, and it will start counting. As soon as it receives a different 11-bit message which says stop counting, it'll understand the value it has just received. So this anchor symbol design is a crucial part of Y Chronos because that is the one that determines the start and stop duration, and that's the one that determines the energy consumption. So like I said before, if we want to use Y Chronos for an energy efficient system, we want to choose an anchor symbol that's small and therefore it consumes low energy. The second metric that we are interested in is long range communication, right? And we saw that if our bandwidth is smaller and smaller, we can go longer and longer distances. And since we have separated time on air and the duration of my message, Y Chronos is able to use ultra narrow band communication without significantly affecting battery life. So the curves that we see here are when we increase our bandwidth, the noise floor of the wireless medium is increasing, but the receive power is relatively the same. So the signal to noise ratio would decrease if my bandwidth keeps increasing. But since the message that we are sending is so small, the impact on the noise floor is much smaller for Y Chronos, and therefore we are able to achieve distances longer than few kilometers, and to some extent tens of kilometers in theoretical evaluation using ultra narrow band transmission without affecting battery life. And the third factor that we were interested in for LPWANs is wide area deployments, which is allowing multiple devices to coexist simultaneously in a single network. So I do apologize if you're familiar with some of the medium access control protocols, and I'm repeating myself here. But one of the most commonly used medium access protocols, which is how multiple wireless devices coexist and share the wireless medium in LPWANs, is called Aloha. So Aloha simply means if I have some data to send, me as a sender, I would send as soon as I have that data. So it simply is, I don't care about any of the devices in my neighborhood, and I'll send whenever I have data to send. This is in contrast to how Wi-Fi works, which is a listen before talk, more polite wireless communication, where Wi-Fi devices typically listen to the channel and speak only if no one else is speaking. So the reason LPWANs use Aloha is Aloha doesn't coordinate with other devices, and therefore it's energy efficient in that I don't have to spend any energy in listening to the channel, sensing if anyone else is talking at the same time as I am. Instead, I'm going to wake up only when I have data to send and send it over air. For that energy efficiency, typically most LPWANs use Aloha. So in an Aloha network, because we don't worry about each other's transmissions, there is a probability of collision when two devices start transmitting anywhere in between their data transmission. So if sender 2 started transmission anywhere between the start of sender 1's and end of sender 1's transmission, these two packets are going to collide. So just by the design of Y chronos, which is to send data in the time interval between transmissions, we are able to reduce this probability of collisions significantly. The reason being, Y chronos is not going to be on for most of the time. A Y chronos transmitter will wake up, send a start message, and until its clock timer expires, it's not sending anything. The duration between my start and stop, I'm not using the wireless channel. So basically I'm saying everything just by remaining silent. And because I'm remaining silent, a different sender can start its anchor symbol transmission, which is start and stop, and either complete or send a stop after my stop. But the probability of both of us having the starts at the same time and stops at the same time would be much lower than what I would have with a conventional modulation. Once again, the key point here is all the transmissions are smaller in duration for Y chronos as opposed to longer in duration for conventional modulations. So with the time interval modulation that we spoke about, we were able to separate time on air from the duration of a message, which led us to achieve long range by still using low bandwidth, and low bandwidth led us to use long range. But because our overall packet on time was extremely small, we were still able to get long battery life despite getting a small time on air. And because our time on air was small, we were able to reduce collision significantly, which led us to get all three features simultaneously. But one of the things to note here is, because I'm sending data over the time between two transmissions, now the longer my data is, longer is the wait period between two transmissions. So if I were to send a binary sequence of my message, say I have a data 100, and I were to send that message as a sequence of bits, it would take me log to the base 2 of 100 bits to send over air. Whereas Y chronos would need the integer value, which is 100 clock cycles. So for every bit of information, additional bit of information, my average wait time would double. So my wait times would exponentially increase. And that's the cost I'm paying for low energy and long range for large scale deployments. So Y chronos is not a high data rate protocol, in that if I have applications which have more than tens or hundreds of bits of information to transmit every few seconds, Y-Chronos would always be waiting in sleep period because it's sending a start and exponentially waiting for the data, the clock timer to end. So all the protocol and the design that we spoke about in the last few slides, we implemented almost all of them using commercial off-the-shelf radios that we see here. So the red microcontroller that you see is MSP430 from Texas Instruments. It's a low-power microcontroller. And here is an off-the-shelf wireless transceiver that lets us transmit something without any protocol, and therefore we can implement our own protocol. The complementary receiver was connected to a laptop for real-time data collection. And we operated mostly in 915 megahertz to reach long distances at a bandwidth of few kilohertz and a few dB transmit power. So just to get a sense of what our implementation would look like in our microcontroller or protocol implementation, as soon as we read data, our device is mostly in sleep. So y-axis is current here and x-axis is time. So the current drawn is in nanoamps because everyone is in sleep. Periodically the device wakes up, it reads data from the sensor, and as soon as it reads data from the sensor, my radio module is woken up, it ramps up, the current ramps up, and I would transmit my preamble or start message. Once I transmit my preamble, which is the current is at its highest because my radio is on, as soon as I send my preamble, I'll immediately go back to sleep because I'm going to send information by remaining silent, right? So I want to conserve as much energy as I can. So when I'm in the sleep mode, when I'm simply counting for clock timers, I put my microcontroller, radio, everything to the lowest power consuming mode possible, and simply have a timer that's on and a timer interrupt that counts for whatever is the amount of information I want to send. So if my sensor read a data 100 units, then my timer interrupt is set to a value of 100 clock cycles, and everything else goes to sleep. So as soon as the 100 clock cycles expires, my transceiver, my radio module is woken up again. It ramps up and it transmits the stop or a post-amber signal, and that repeats continuously. So if you can see from this current versus time graph that the current drawn by a Y-Chronos device is the area under the curve would be the energy consumed by a device is only dependent on the duration of my preamble and postamble. As opposed to a conventional modulation, if you notice here, the current is high throughout my packet transmission. So technically Y-Chronos is sending data in this entire duration, right? But during my data transmission, I'm sleeping, whereas conventional modulations have to be on during data transmission. And it's the difference in this area under the curve here versus these two that leads to energy efficiency for a Y-Chronos device. But so far, we've been thinking about Y-Chronos in an idealized network where there are no clock errors, there are no timing errors, but there's plenty of room for errors in a Y-Chronos system. Some of the errors are processing time error in my microcontroller or processing time error in my transceiver, in that I would like my transceiver to wake up exactly here, but I thought it woke up exactly here. But I miscalculated my processing time and I ended up starting a little late. So that was going to affect my counting time between the preamble and the postamble. A second room for timing error is the variations in this ramp up time of my radio modules. And the third is a skew in my clocks, which is I expected my timer interrupts to wake up after 600 cycles, with the assumption that each cycle is, if I'm using a 10 kilohertz clock, each cycle is 1/10, 0.1 milliseconds. But if there is a skew in my clock, which is if it's not measuring, if it's not going up every 0.1 millisecond. Instead, there's a plus or minus 10% error in my clock counts. That completely messes up my data. So instead of receiving a data of 100, I would count that as 99 or 101. So some of the solutions we came up with for, I'm not discussing all the solutions, but a simple solution we came up with was just to introduce redundancy. If there is going to be clock skew, meaning if I'm going to count 99 as a 98 or 101, let's just map multiple clock cycles to one data. So if I want to send a data value of 50, I would assign a clock cycle 50, but I wouldn't assign clock cycles 49 and 51 to any other data message, because if my receiver receives anything between 49 and 51, I would see that as 50. Similarly, one other scope room for error is my start or stop message being completely lost. So we proposed few solutions to address some of these timing errors when they are bounded, in that we know the upper bound of these errors. So there's still some of the ongoing work is to see if they are unbounded errors, how do we address that? So you might be familiar with some of the areas that we're showing here. We did outdoor experiments. This is Camp Randall Stadium. We performed experiments in and around campus, ranging from few hundreds of meters all the way to close to a kilometer distance. And the range here, we did not go beyond 1 kilometer, is mainly due to our hardware limitation, in that our radio module, the module that we chose, we cannot transmit beyond 13 dBm, and that limited our distance. But in theory, we estimate the distance to go as high as 10 kilometers without much change in the implementation. So we would have this transceiver, the transmitter, connected to a soil moisture sensor deployed at one of the ends, and a receiver with a laptop deployed at the other end. And we measured this information, measured the data every few seconds, and transmitted wirelessly to the receiver for a few minutes, and going up to a few hours in some experiments. And we collected this data in real time. And the metrics that we evaluated were exactly the metrics of interest, which are distance, energy efficiency, and the number of devices we can accommodate. So we compared the energy efficiency as a function of the battery life of a coin cell battery. We used a 500, I think I'll have to confirm that. I think we used a 500 milliamp hour battery, and estimated the battery life by measuring the average current and therefore the average energy consumption of our entire module. And we compared the estimated battery life of our proposed method, which is Y chronos, the red dotted ones, against LoRa, one of the most popular LPWAN technologies out there. And LoRa has few settings. So we compared with the best, one of the settings which is best for energy consumption. Even the best LoRa setting for energy consumption, which is the red curve, was approximately 2x lower than that of Y chronos. And this is particularly because LoRa radios have to be on for the entire duration of transmission, and the longer and longer our messages, lower and lower is the battery life. And we also compared against SigFox, another popular technology, which is much longer range communication, but it sacrifices battery life. One of the other metrics that would combine wide area networks, the impact of wide area networks and average data rate is goodput, which is the network throughput that we can get for different network conditions. If I have 10 nodes, 100 nodes versus 1,000 nodes, the larger and larger my network is, what is the maximum data rate that I can get? So although Y chronos can only support few tens of bits per node, here we are plotting the network throughput, which is the average bits per second of the entire network. So the reason, although Y chronos individual data rate is smaller than that of LoRa, as a network, Y chronos outperforms LoRa, because LoRa devices, when they start when we have more and more LoRa devices, multiple LoRa devices would collide, and collided nodes would lead to incorrect packet receptions, and therefore they were not correctly received at the receiver, decreasing the goodbye. So we performed experiments with up to 10 devices due to, of course, budget constraints and resources available. We could not go all the way to hundreds of devices, but this was a simulation result. Our ongoing effort is a collaboration with Department of Soil Science here in UW to implement our protocol on real fields and collect data over a long period of time. So we've successfully managed to put together all of our protocol with some sensors to be deployed in one of the research fields to measure these sensor modules over a few months of time. So based on in-lab experiments, our battery life is significantly higher than existing technologies, and we are confident that deploying in real world and real field deployments would give us more confidence about our approach. So that's our ongoing effort. So just to refresh our memory about the state of the art and what we wanted to achieve was long range, low power consumption at the cost of course, data rate. And Y-Chronos is one such solution for that. I want to just quickly talk about one more problem that we are working on and are interested in, is to explore more in the area of LoRa. So LoRa, if you guys remember, we talked about LoRa as one of the popular technologies that have come up to address the needs of LPWANs. So in our, as you see in this figure, LoRa does achieve long range and is relatively low power, but it fails in the scale of the network. A LoRa network can, as we go beyond few nodes talking simultaneously, LoRa node fails. So current deployments overcome this problem by saying a LoRa device will not, by limiting its duty cycle, meaning a LoRa device will not transmit regularly. A LoRa device is only allowed to transmit once every few minutes or hours, depending on the application. So one of the other problems that we are working on is to allow multiple LoRa devices to talk to each other simultaneously. So I won't get into the specifics of that, but our proposed solution here is to understand the fundamentals of LoRa transmissions and seeing how we can leverage both timing information and frequency information of LoRa packets to infer data despite packets being collided. So our interest here is to say, when multiple LoRa packets collide, can we still understand what was sent in each of those nodes? And we succeeded in inferring up to 8 packets in parallel. So that significantly improved LoRa's overall network throughput. So just want to show one result here to say that, so if you look at the purple curve, that's a standard LoRa device that we buy from an off-the-shelf, any of the companies that we can buy LoRa transceivers from. As we have more and more packets that we send in a given second, LoRa's throughput decreases, whereas our proposed interference cancellation method is able to infer most of the packets despite collisions. So effectively, we are able to increase the data rate, which was a problem with LoRa. In turn, it will increase the bubble size of the LoRa network that we talked about. So once again, here our goal was to increase the number of devices that can be accommodated in parallel in a technology like LoRa, which already supports low power and long range. So we've been looking at few technologies that are in LPWANs and trying to address and ask the question of coexisting needs, low power, long range, and large scale, and of course, low cost. So I want to conclude this talk by saying some of the open-ended problems that we are looking for ahead and looking into are going from down below. Some of the LoRa techniques that we've developed and other research teams and companies are developing. LoRa is an ongoing, the research in LoRa field is ongoing and it's continuously developing. So we are looking into a cloud-based LoRa decoder similar to Cloud RAN that are popular in 5G technology to see if we can implement a LoRa decoder in the cloud that would further reduce the cost of LoRa infrastructures. And most of the discussions that we have had today and that are being asked in the community is limited to one network, which has one gateway and hundreds of devices talking to that gateway. I think going forward and into the future, we have to think about multiple gateway infrastructures. If we have to cover hundreds of acres of a field, we cannot survive with a single gateway. There will be multiple gateways. How would we design medium access control protocols when we have multiple gateways, and potentially data-driven or machine learning approaches to optimally encode data in this timing interval modulations, optimal approaches to infer packets despite collisions, and more physical layer techniques using data-driven approaches. So with that, I think I'll pause and I'll stop sharing my screen and go look at some of the questions. And of course, we can also have questions over the discussion here as well.
Thanks for the talk. I have recorded the questions. I will read them to you, and you could perhaps answer them. First one was from Malcolm Lund to everyone. Do you use solar for the transmitter and processor to manage the power and send data when power is present? I recall some Campbell Scientific sensors and transmitters for weather and remote that use solar and were not low power of recent times, but did send as solar allowed to charge the battery.
Oh, that's a really good question. And I think one of the first steps that we took into account was to see if we were using solar powered transceivers, will that solve the problem of low power wide area networks? So the challenge there was, in addition to cost, of course, availability of solar power, but also form factor, in that if we are relying entirely on solar power to drive these wireless devices, the size of the form factor of the solar panels needed were high, and that limited the usability of different sensors, different deployments too. But one of the biggest factors there was cost of solar cells. So if we were to deploy hundreds or thousands of devices, that added up, the cost per device added up, and that affected the deployment's feasibility on top of everything else. But it is feasible to have solar power, just that they were not the most cost-effective ones.
Thank you. A second one, question from San Rotter was the topology for low power wide area networks, node-to-node paths versus one central node, mesh versus star topology.
Yeah. So I think the question is to see what are the pros and cons of mesh versus star, is it? If I'm understanding that right?
San could probably explain, ask the question a little bit better, but that's what he wrote. So.
Okay. Sure. Yeah. So
he said yes. That was correct.
Okay. So like I said, the star topology versus mesh has been studied in wireless community in depth, but the major driving factor for star topology is cost. So when we have a mesh topology, we need multiple devices to coordinate with each other, which would reduce the energy consumption of which would increase the energy consumption of each of the devices. And when we have a mesh network, we will need multiple intermediate devices to coordinate these transmissions. So you'll have multiple gateways that have to be constantly powered to coordinate with each other. And that's why a lot of LPWANs are favoring star topology, because in a large network, we just have to worry about one gateway which needs to be constantly powered. The smaller IoT devices are battery powered. So like I said, again, cost drives towards star topology, and also the fact that deployment and maintenance would be easier with a star topology. I hope that answers your question.
Okay, another question was from Connie. How is error correction handled? What is the susceptibility to interference? If someone keyed a radio or connected a cell phone, would it overwhelm the front end of the device?
Oh, that's a really good question, and I think that's something we did take into account when we are looking into this, and that's a problem when we have our real world deployments too, right? So again, when we think of LPWANs, a lot of technologies are going towards narrower and narrow band communication. So the frequency band for a Wi-Fi, for example, would be 20 megahertz. Cellular network would be hundreds of kilohertz, or even more depending on our the kind of LTE that we use. But an LPWAN would go for tens of hertz in some technology, or a maximum of 500 kilohertz. So the first consideration there is, because our bandwidth is narrow, we would be less susceptible, we would be more resilient to interference, because we would expect interference across multiple frequency bands. So if we have an interferer coming in exactly at the same band that we are working on, then that would be a problem. And one of the ways we address that in Vychronos is we operated in as narrow a band as we can. And that would negatively impact our energy, but because of our design, the start and stop are small, narrow bandwidth wouldn't significantly affect. But beyond Vychronos, LoRa, SigFox, NB-IoT, most of the technologies use narrow bands, and narrow bands rely on narrow bands resilience to interference to overcome that.
Thanks. The next question was actually from me. I just wondered, if you have a number of devices sharing the same frequency, there must be some difference in the preamble and postamble codes. There must be some bits included into. How does that add to the sequence length for those?
Excellent question. And I don't think I had a slide on that, but the anchor symbol that we saw, the preamble and postamble, the length of that, or the bit sequence itself, was uniquely assigned to each device. So we looked at a curve with probability of false positive and false negatives. On top of that, we also had one more curve, which is to say, if I have larger networks, if I have 1,000 devices, the least number of bits I need is 10 bits. So on top of those 10 bits, how many can I assign for preamble and postamble? So those were also taken into account in our design, and the energy efficiency figures that we saw included these unique addresses. So basically, we assigned each device a unique bit sequence. But that is one of the areas where we have open-ended questions asking, is there a better way to assign addresses to devices? Meaning, can we use frequency division multiplexes, assign some devices to one frequency and another set of devices to another frequency, and have them coexist? So there's room to improve the number of devices and improve their energy efficiency by bringing in many protocols, many modalities of MAC protocol. But it's an important question that we looked into, and we continue to look into as well.
Two questions from San also. Did you monitor the ambient RFI during the experiment on campus? And then he actually throws in a little thing here saying that the latest stats from Ham Radio Club Log website shows that over 50% of contacts in 2020 were via the FT8 coding. And I guess he wonders if you knew about FT8.
I don't know about FT8, to be honest, but regarding the ambient RFI, that we did monitor that, and that's an important factor in the design of our system. In that, when our bandwidth is narrower and narrower, the amount of noise that we receive, our noise floor would be smaller and smaller. So when our bandwidth is narrow, our receiver sensitivity would improve as well. And that's why we would prefer to have a narrow bandwidth. So one simple way that we overcome the impact of ambient RFIs simply to operate on a narrow bandwidth. So that increased our range and improve our receiver sensitivity. I don't know about FT8. I'll look into that and maybe I can get back on that later.
Finally, from Roger Gopal sent a question. Can we isolate devices due to deviations from data integrity point of view and also rank devices and optimize as to wake time span?
I see. So is the question, let me just repeat the question to see if I understand that correctly here.
He sent it. It's the last one in the chat function. You can probably read it from him directly, but it says, can we isolate devices due to deviations from data integrity point of view and also rank devices and optimize as to wake time span?
I see. So this is to say multiple devices could have different integrity as reliable, adding reliability to the information and prioritizing how we send. Oh, absolutely. I think one of the simple methods that we saw was to overcome clock skew was to assign some form of reliability by adding redundancy, right? So that was the simplest way of ensuring data was transmitted correctly, but there's plenty of error correction codes. And on top of that, coding techniques that improve the reliability of our transmission. And unfortunately and unfortunately, a lot of research hasn't gone into error correction codes and reliability for timing interval modulation. So the fundamental timing interval modulation that we saw today, it's not entirely new. I think pulse position modulation, this is a variant of pulse position modulation, which is quite popular in optical networks. So but in optical networks, reliability hasn't been studied too much. So fortunately, we have a lot of problems that we can explore now. But those are definitely ways to look into to see the statistical differences between the transmitted data and assigning them different priorities. Yeah, I think short answer to that is yes, we should. There is room to work on that direction. But it's an answer.
I think that completes the questions that were submitted. I'm going to open it up for people to talk to you verbally. But first, I'm going to ask you another area. You know, one of the groups on campus is tracking wildlife. There's the wildlife group that does. They use the simple ping and then use radio direction receivers to try to figure out where the animals are.
Yeah.
The newer technology includes GPS in it as well. So a question would be, could you use your modulation technique along with the fact that you don't move much in position to sort of encode the positional and the time, the data functions as well?
Oh, I think that's definitely room to do that. So, like I said, the first collaboration that my team has started with soil science was to look at static sensor data. But some of the conversations that we've had since then have been with dairy in the Department of Dairy Sciences to measure movements of cattle. It hasn't materialized just yet, but there's plenty of scope to see to implement a low power, low data rate communication algorithms such as this to track movement of wildlife. Domestic life for sure. Wildlife needs more coordination because the range of communication is much longer, so needs some more study. But that's absolutely possible.
Okay, and with that, I'm going to open up somebody's trying to talk. Let me just open up the meeting so that all may unmute yourselves and ask the question. So
I want to
Dennis,
ask a question about the marketplace's effect on the topology that you were talking about, and if different marketplaces of having more devices or less devices would affect what the topology is and drive you to different, more to energy harvesting or less to energy harvesting, depending upon who the client is?
Oh, that's an interesting question. So, so far LPWANs have looked at stars. So you're suggesting, depending on the application, the energy efficiency part could be still achieved with energy harvesting, but we can improve the range by adding more devices in the network, is it? I think that's an exciting idea and worthwhile looking into. So one of the approaches that my student is currently looking at is so far we've used mostly battery to power our transmitter and the wireless device. If we were to use I think RF energy harvesting in the real world or outdoor scenarios is very hard. So energy harvesting in the sense of vibration-based energy or wind energy harvesting, even if it's small, that might be sufficient to power the device. So that is one of the directions that we've looked into. But I think what you're recommending is a great way to go forward for LPWANs to bring together energy harvesting and mesh technology to cover a wider area. Absolutely, I think this is certainly possible and would be worth looking into.
I posted some URLs for both the FT8 and Whisper, so I hope to proselytize amateur radio to you and your students.
Oh, sure. Yeah, I'll certainly follow up with you after looking into these links. Thanks so much.
And I have recorded them all. I'll send you a document with all the questions and the links in them. So
Thank you so much.
Any other questions? I'm sorry. I'm sorry I interrupted, Dennis. Go ahead.
You're on an ISM band, 902 to 928. That's 26 megahertz wide.
Yeah.
Do you transmit all on one frequency, or do you separate multiple frequencies for transmission and then let the receiver sort it out?
Right. So that's a great question. So far, we've not explored the entire band. Yes, we are operating in the ISM band, but so far, all our experiments and the design that we have is operating on a single frequency or a single channel, which is only 100 kilohertz wide though. So we operate on a center frequency 915 plus or minus 50 kilohertz, which is where one of the next steps that I talked about was to bring in frequency division multiple access, where we let different pockets of devices use different center frequencies within this 26 megahertz, and the receiver sort out different devices by listening to the entire band. That's certainly a next step, but we haven't done that just yet. That's the direction we are going towards.
Okay, good.
Well, to follow up on Dennis's question, have you looked at spread spectrum and the IEEE honor of Hedy Lamarr?
Oh, yes. So one of the, I didn't get to go into details of LoRa. So one of the innovations that came up from LoRa is the use of chirp spread spectrum. I think the one you're referring to would be OFDM, I think, or I think that would be the closest to OFDM, one of the spread spectrum techniques. And LoRa uses a different spread spectrum called chirp, which is similar to radar. That is another physical. So when I was talking about some of the LPWAN technologies, I think a rethinking is happening all the way from modulation techniques, medium access controls, how the architecture is all the way in the networking stack. So on the physical transmission, people have started looking into new spread spectrum techniques or implementing existing spread spectrum techniques on a narrow bandwidth of operation. Yeah, I think just to answer your question, it is one of the approaches that LPWANs do take. And it's a fertile field to look into other spread spectrums.
Okay, any other questions?
Yeah, hi, Bhuvana. Thank you for presentation. This is Zhi Chao from Michigan State University. And
Hi.
I'm also doing the research on the LoRa networks currently. Yeah. I have two technical questions for you. The first is, for the wireless, does the multipath interference degrade the performance of wireless? And the second question is for the packet collision cancellation. Do you record the ISNR of the packets above the noise floor, or just the below noise floor packets collision can be resolved? Thank you.
Oh, sure. Thanks so much for your question. So the first question was about micronoise and sorry, just can you repeat that question? I thought
so yeah, because you know, in the
multipath. Sorry, yeah.
The multipath, maybe we have the multipath interference. That's
okay.
Multipath interference degrade the performance.
Yeah, got it. Thank you. Sorry, my bad. So your first question about multipath is something we certainly looked into. I didn't get to talk about that. So two-part answer to that, I would say. One is at lower and lower frequencies, because our wavelength is much higher, the impact of multipath transmissions is lower as compared to Wi-Fi or millimeter wave, which has much higher frequency. So just to begin with, the impact of multipath is smaller for sub-gigahertz bands. And secondly, when we are transmitting a much shorter message, which is the start and stop messages in micronoise are a few bits and not tens of bits, the impact of multipath is much lower because the packet duration itself is small. The data is long, but the amount of information that we are sending over air is small, and therefore the impact of multipath on each of that operating at narrow bandwidths is relatively much smaller. So when we are operating at 100 kilohertz, each bit, each symbol duration is 1/100 kilohertz, right? So we'll have to be tens of kilometers, or I think we calculated the impact of multipath to even have slight effect beyond 30 or 40 kilometers. So, and even then, it wasn't large enough to affect the decodability of the message. So that would happen even beyond 40 kilometers. So at reasonable distances of communication, the impact is small. The second question is about LoRa concurrent transmissions. Although I didn't talk about it, the solution that we developed called concurrent interference cancellation, we were able to decode LoRa packets below noise floor as well. I think we went, we were able to decode up to 7 nodes in parallel, where some of the nodes were -8 dB, operating below noise floor at -8 dB. I'd love to talk to you after this meeting or some other time to go over that work. But yeah, that was where we were at by the end of
Okay, thank you.
Thank you so much.
No other questions? I think what we'll do is I will stop the recording of the meeting now. If people want to hang around and chat a little bit afterwards, we'll leave the meeting open till about 8:30 and then I'll close it. So thank you very much for your talk, and thanks all for attending and the good sets of questions, and have a good evening.
Thanks for inviting me in, and this is really fun to be a part of, and I'd love to be involved in the future with all of you.
Yeah, I want to thank you as well. It was a very good talk. Excellent.
I'd like to thank you from the old farts and the LM, whatever acronym we use. And any questions about amateur radio, I'd be happy to help you with and introduce your students to some of the packet modes. And Malcolm added a mode that I left off, but there's many digital modes. And recently I find that Morse code is faster a lot of times than all the other digital modes in these de-expeditions. I am challenged, but they go over 40 words a minute, and they clip off pretty fast.
Okay. I'll definitely take up on that offer. I think I'll ask Tom for your contact, and I'll reach out to you later today or sometime over the weekend. Thank you so much for your help.
Well, thank you for an excellent presentation, and excellent storytelling for us academically challenged after all these years.
I
What do you
find that
use?
hard to believe, but thank you so much. About the second half, yeah, but thanks for saying that.